Hi, welcome to all. Today we are going to discuss one important concept, exponential function. Actually, exponential function, this concept belongs to third unit. So based on this concept, in the year 2020, 6A, one theorem will be asked. To prove that theorem, let us see some basic concepts. See, the Euler's number E is defined as E is equals to summation n is equal to 0 to infinity 1 by n factorial. So actually you already know this in your series concept, and also E also be defined as alternatively E is equals to limit n tends to infinity 1 plus 1 by n whole to the power n. So let us discuss some important points. For any complex number z, we define E of z is equals to summation n is equal to 0 to infinity z to the power n by n factorial, taking this as equation number 1. So expand equation 1, we get E of z is equals to 1 by 0 factorial plus z by 1 factorial plus z square by 2 factorial plus and so on. For this, put z is equals to 0 in equation 1, we get E of 0 is equals to 1. So this is one point. Second point, take z and w are two complex number, then we define E of z plus w is equals to E of z and E of w. So remember this point is very useful to prove this theorem. What is the theorem statement? Let e to the power x be defined on by e to the power x is equals to summation n is equal to 0 to infinity x to the power n by n factorial. Then prove the following. First one is e to the power x is continuous and differentiable for all x. Second one is d by dx of e to the power x is equals to e to the power x, and e to the power x is strictly increasing of x, and also prove that e to the power x is greater than 0. Fourth one is e to the power x plus y is equals to e to the power x into e to the power y. Fifth one, e to the power x as tends to infinity, as extends to infinity, and e to the power x is converges to 0 as extends to minus infinity. So this is the statement. So let us prove one by one. So first let us take what is given. Given e to the power x is equals to summation n is equal to 0 to infinity x to the power n by n factorial. I am taking this as e to the power x because here I am defining E of z is equals to summation n is equal to 0 to infinity z to the power n by n factorial. Here z is there, so I am defining as e to the power z. So here x is there, therefore I am defining E of x. So let us prove first one, e to the power x is continuous and differentiable. First I am proving e to the power x is continuous. First prove e to the power x is continuous. By the definition, basic definition, limit h tends to 0, e of x plus h is equals to e of x. To prove this, then e to the power x is continuous. Now consider this. What? E of x plus h is equals to e of x into e of x according to this property. So for this, take the limit as h tends to 0 both the side. Limit h tends to 0, e of x plus h is equals to e of x into limit h tends to 0, e of x. Now we have to find this value. So limit h, e of h is equals to 1 plus h square by 2 factorial plus h cube by 3 factorial plus and so on according to this. So for this, take the limit as h tends to 0, we get 1. Then equation star becomes limit h tends to 0, e of x plus h is equals to e of x. So I am proving this. Therefore e to the power x is continuous for all x. In the next video I am going to prove e to the power x is differentiable.